Hello everyone, welcome to Sai Tutorials Jamkandi. So in today's class, uh, let us discuss about the third chapter of the second PUC physics, that is moving charges and magnetism. See, in moving charges and magnetism, I have discussed some introduction part of this chapter about how an electric charge is going to happen in the case of magnetic field or in the region surrounding a current carrying conductor. So what is electric charge in an electric field and moving electric charge in a magnetic field and moving a electric charge. So how it affects and how it causes, and also the magnetic force. I have explained briefly about magnetic force on a charged particle moving in a magnetic field, and also I have discussed about the Fleming's left hand rule. So let me revise Fleming's left hand rule once again. See, stretch the first three fingers of the left hand such that they are mutually perpendicular. So if the forefinger is in the direction of the field, the middle finger is in the direction of velocity of the positively charged particle, then the thumb gives the direction of the mechanical force. So in today's class, let me discuss about motion of a charged particle with velocity v bar and perpendicular to the b bar. Okay, so let us discuss. See, motion of a charged particle with velocity v bar, that is perpendicular to the magnetic field v bar. How it is going to be happen? That is the motion of the charged particle. So it is having some kind of magnetic field v bar and also v bar. See, consider a positively charged particle. So let us consider a positively charged particle moving in a uniform magnetic field. Okay, so let us consider a positively charged particle moving in a uniform magnetic field when the initial velocity of the particle is perpendicular to the field. Okay, so some kind of charge it is. Okay, some kind of charge. It is moving in a uniform magnetic field, that is v bar. So the initial velocity, so whatever the initial velocity of the particle, that initial velocity is perpendicular to this magnetic field. Okay, so let us consider a figure. In the figure, the magnetic field is perpendicular to the plane of the paper and inwards. See, if you consider the figure, okay, see, these are some kind of positive charges, is it or not? Okay, so here it is having the charge plus q. It is having the charge plus q. See, this direction in the denotion this direction, I mean this denotion is nothing but the inwardness. Okay, inward. Okay, see here, this thing and this thing. So whatever the denotions are there, no, that are inward. So consider a positively charged particle moving in a uniform magnetic field. That is, let us have a consider that plus q is a charge here, which is moving with a uniform magnetic field b bar. Okay. So when the initial velocity of that particle is perpendicular to the field, so that the initial velocity is perpendicular to the magnetic field. So that is inward. Okay. Now the particle moves in a circular path whose plane is perpendicular to the magnetic field. Suppose this, let us consider this charge. This charge is moving in a circular path. Okay. So it experiences some kind of magnetic velocity. Okay, it experiences some kind of velocity. That velocity is perpendicular to the magnetic field. Okay, that is inward pull. So whatever the charge or whatever the particle is moving around the circle, I mean in the circular direction, it is having some kind of velocity, is it or not? So it is having some kind of velocity. So that velocity, the whatever the field is moving, that is inwards. Okay. So it is inwards. So if you consider the plane of paper also, okay. So perpendicular to the plane of the, if you consider the circular plane of paper, here whatever the charge is moving around the circle, so it is having some kind of velocity. That velocity is perpendicular to the magnetic field. So the centripetal force is given by this thing. There is an inward force, is it or not? FB here, it is an inward force, that is centripetal force. So that can be written as mv square divided by r. So it is provided by the magnetic force. So that is provided by the magnetic force, is it or not? Okay. So where r is a radius of the circular path. R is a radius of the circular path. So they have derived r from this equation. Okay. They have derived r from this equation. Now, the angular speed it is denoted by omega. Okay. Omega, it is equal to velocity per unit radius. I mean, v by r. So if you substitute r value in this equation, we will get qb divided by m. And also the time period of the circular motion, that is t, is equal to 2 pi r divided by v. So where if you substitute r and v value here, you will get the time period, that is 2 pi m divided by qb, and frequency, that is f, is equal to qb divided by f 1 by t. Frequency, it is 1 by t. So it is given by qb divided by 2 pi m. So let me derive it neatly. Okay. See here. Suppose if I consider a charge, this is plus q. Suppose if I consider this charge plus q and this is plus q. So it is moving in a circular path. It is having some kind of velocity v bar, and that force, that is inward force, it is equal to, I mean this direction. Okay. This is v bar. It is having an inward pull. That force is equal to magnetic force. Okay, suppose it is in, the force is like this, it is inward, the velocity will be perpendicular to the that velocity, that magnetic field. Okay, here also same. This is fb, this is also fb, and this is velocity. So suppose I have considered the centripetal force. Centripetal force, that is equal to mv square divided by r, is it or not? Okay, the centripetal force, that is given by mv square by r. So that is equal to the magnetic force, that is qvb. Is it or not? Now, no. So if you calculate r value here, one v and another v get cancelled. That is mv divided by r is equal to qb. Suppose you will get the R value here, that is mv divided by qb. This is the R value. Is it or no? Now, this is the R value here. Radius of that circular path. Now, the angular speed. Okay. Angular speed here. So we got the R value here. Angular speed, that is omega, can be written as V divided by R. Okay, so if you substitute these values, you will get QB divided by M. The time period of the circular motion, that is 2 pi R divided by V. So if you substitute R and V value in this case, you will get the time period, that is 2 pi M divided by QB, and the frequency of that particular motion of a charged particle, we will get QB divided by 2 pi m. This is the frequency. Okay. Now, see here the conclusion. Okay, this is the conclusion. The conclusion for this, whatever I have derived here, that is the angular speed of the particle. Okay, the angular speed of the particle, the period of the circular motion, time period t, and frequencies of the rotation do not depend on the translational speed of the particle or the radius of the orbit for a given charged particle in a given uniform magnetic field. So this principle is used in the design of particle accelerator called cyclotron. Okay, this is one kind of application or the for the whatever the resources, I mean whatever we have used in terms of the motion of the charged particle in terms of velocity and magnetic field. So we will say that this angular speed of the particle, so whatever the time period and also the frequencies of the rotation, that will not depend on the translational speed of the particle. Okay, the translational speed of the particle or the radius of the orbit, or for a given charged particle, or for a given charged particle in a given uniform magnetic field. So in that condition, this principle can be used to design a particle accelerator. See, this is called as a cyclotron. Okay, this is called as a cyclotron. The device, whatever the, if you want to design the, what are the particle accelerator. Accelerator means for stimulus, I mean instantaneous stimulates to the whatever the particle. Suppose if I consider this is a conductor, if the particle is here, it is to move from this place. So we need to accelerate this particle. Suppose by heating, I mean suppose if you provide the heat for this particular electron or particular particle, that electron will accelerate and move towards to the next place. Okay, is it or not? So in such case, we will use the particle accelerator called as a cyclotron. Okay, this is called as a cyclotron. So what is cyclotron? You can just glance here. This is not for, actually this is not for your syllabus. So let me tell something about it. So what is cyclotron? Okay, see, cyclotron is a device. It is used to accelerate charged particle to, to very large kinetic energies by applying electric and magnetic fields. So if a particle, okay, it is a particle, I need to accelerate this particle. Okay, I need to accelerate this particle. So what is the criteria to accelerate this particle? So this phenomenon can be done with the help of the device called cyclotron. Okay, cyclotron. So how only a device, it consists of some kind of criterias, right? So it is having some kind of kinetic energies. By applying the electric field, we can just accelerate the particle. So in that condition, we need to apply the large kinetic energies and also the electric and magnetic fields. Okay, I have said here, if I if I apply heat energy, or if I need to accelerate that particle, if I need to increase the temperature of the particle, I mean medium, or I by applying the kinetic energy or applying the electric and magnetic fields, we can easily accelerate the particle whatever present in the conductor. So in that case, the cyclotron will help easily. Okay, cyclotron is a device that is used to accelerate charged particle to very large kinetic energies by applying electric and magnetic fields. Okay, so this is a kind of device or application type of the motion of charged particle. So that is cyclotron. So give an example for a device that will accelerate the particle. You can write the cyclotron. It is answer is cyclotron. Okay, it is. So to accelerate that particle, I need to apply some kind of electric as well as magnetic fields and also the kinetic energies. Okay, so this is what about the some kind of application. Okay, or a kind of principle. So this is a schematic diagram of cyclotron. So there for your syllabus there is no need to write the what is cyclotron, and in fact it is not there for your syllabus. So I just glanced with whatever comes under your syllabus. This is just a part of syllabus. Okay. So no need to explanation of the what is the design and what is the criteria or what is the working principle of the cyclotron. There is no need to say you. So this is just a device that is used to accelerate the particle whatever present inside the conductor. Okay. So now let me discuss about expression for kinetic energy. Okay, expression for kinetic energy. So we all know that what is kinetic energy. Okay, we all know that what is kinetic energy. See, it will comes under the kind of criteria that is motion. Is it or not? Okay, it is comes under the criteria that is by virtue of the motion. By virtue of motion. So let us derive an expression for kinetic energy. The maximum kinetic energy of an ion as it emerges from the cyclotron will then be. Okay, so let me derive this expression. Okay. Kinetic energy. We all know that, okay, kinetic energy is equal to half mv square. Is it or not? Okay. Now, if you substitute v value here, what is v here? We got from equation that is qbr divided by m. Is it or not? Now, if you substitute the kinetic energy value, you will get m into what is v here? qbr divided by m whole square. Okay. Now, that kinetic energy will become, if you square the remaining terms, q square, v square, r square divided by m square. Here 1m get cancelled. We will get q square, v square, r square divided by m. So this is the kinetic energy. This is the kinetic energy. Now, this is a kinetic energy. So kinetic energy, suppose I have R is equal to, we know that kinetic energy is equal to half into q square into b square into r square divided by m. Is it or not? But we know that r is equal to mv divided by qb. If you substitute in kinetic equation, in kinetic energy, we will get half, or this will become r square, half q square v square divided by m square v square divided by q square b square. So where mv is equal to p, is it or not? Momentum. So if we substitute, we will get kinetic energy as half q square b square divided by m. Here 1 q square b square, 1 q square b square get cancelled. Okay, so what you will get? That is p square divided by m. Okay, or you will get p is equal to root of 2m into kinetic energy. Is it or not? Now suppose when there are some cases, okay, there are some cases when charged particle of charge q, that is accelerated through some kind of potential difference V. So we will get kinetic energy is equal to Q into V, where V is potential difference. So in that condition, what will happen? R is equal to root 2m QV divided by QB. Or we can also write it as R is equal to 2m Q into V divided by Q square into B square. So 1Q get cancelled. We will get R is equal to root of 2m V divided by QB square. So when a charged particle, these are some cases. It will help you in case of NEET examinations and CET examination. Okay. So accelerated through potential difference V. So we can write in case of potential difference R is, even if you have the problems like if they give you potential difference and magnetic field and mass, so they will give you to find out the radius. So in that condition it will help you. Okay, so this is when charged particle of charge q accelerated through the potential difference v. Now the time period. Now the time period. So we know that time period t is equal to 2 pi r divided by v. So if you substitute the v value here, I mean r value here, you will get 2 pi divided by v. What is r? R is equal to mv divided by qv. Is it or not? Here 1v get cancelled. That is t is equal to 2 pi m divided by qb. This is the time period. Please note down this. Okay, this is the time period. Now coming to the frequency. Please note down this. Now coming to the frequency. That is F is equal to 1 by T. So reciprocal of the time, that is equal to frequency, you will get QB divided by 2 pi M. Okay. Where that frequency is directly proportional to the charge by mass. Now this is the frequency. Now angular velocity. Angular velocity, you will get omega is equal to 2 pi by T. 2 pi F divided by T, you will get omega is equal to 2 pi into, so what is F here? 2 pi by T, 2 pi by T is common here. So what is F? That is QB divided by 2 pi M. 2 pi get cancelled. So angular velocity you will get QB divided by so sorry, if you apply, just a second. Not F here. 2 pi by T itself. So what is T here? So what is T here? QB divided by 2M. So you will get omega is QB divided by M. And omega is also directly proportional to the charge by mass. So these are all of the conditions. Okay. So kinetic energy when charged particle of charge q accelerated through potential difference, time period, frequency, angular velocity. So these are all the some criteria related to the motion of the charges. Okay. Now helical path of a, there are some application type of questions here. See, a helical path of a charged particle moving in a magnetic field. Okay, suppose here it is a helical path. Is it or not? It is a helical path. Say it is having some kind of magnetic field. So I have said you that the velocity of the particle, whatever the particle is moving inside that helical in kind of helical path, so the velocity is always directly proportional, I mean perpendicular to the magnetic field. Is it or not? So that magnetic field is inside the helical path. Suppose if you consider this helical path like this, so whatever the space between inside this each particular helix are there, no? So these are some kind of magnetic field. It is in the direction of magnetic field. Okay. So this is magnetic field B bar. Now the velocity, it is perpendicular. The velocity is perpendicular to that particular magnetic field. Is it or not? So in horizontal direction it is V cos theta, and in vertical direction it is v sine theta. Okay, so whatever the distance between the two helix are nothing but pitch. Okay, so now consider. So if a charged particle moves in a uniform magnetic field with its velocity at some arbitrary angle theta that is less than 90 degree with respect to a magnetic field b bar, the path is helix. So that kind of path is helix. Okay, the axis of the helix is along the direction of magnetic field. So whatever the helix, okay, it is a helical path. So helix, it is having some kind of axis. Axis is in the same direction about of magnetic field. The axis will be in the same direction of the helix, that is along the direction of the magnetic field. But the perpendicular component of velocity, that is v sine theta, whatever the vertical velocity, whatever the perpendicular velocity component of the velocity, that is v sine theta, determines the radius of the helix. Okay, see, if you consider this like this, okay, it will determine the radius of the helix, that is r into mv divided by qb, into it is in the vertical direction, that is perpendicular to the magnetic field. We will write it as r into mv sine theta divided by qb. This is a kind of application type of questions. Okay, so if you substitute the r value here, you will get like this. Okay, now the pitch of the helix, that is p, the pitch, the difference between the two helix, okay, it is called as a pitch. So pitch of the helical path, that is p is equal to v cos theta. Pitch, so okay, uh, that is along the horizontal direction, along the direction of the path of the magnetic field, okay, into time period. So where it is that period of the circular motion, it is given by 2 pi m divided by qb. Okay, the pitch of the helix, that is p is equal to v cos theta into t. So where t is the period of the circular motion, and it is given by t is equal to 2 pi m divided by qb. Now the pitch of the helical path p is the distance traveled by the particle. See, I have told you that the pitch of the particle, helical path, the pitch of the helical path p is the distance between, or the distance traveled by the particle along the direction of the field in one period of revolution. Okay, suppose it is a kind of, if a particle want to move in the helix direction, okay, if a particle want to move in the helix direction, it needs some kind of revolution of time. Okay, period of revolution I mean, we will call it as the period of revolution. So that kind of revolution, we need to have some kind of pitch there. So pitch is nothing but the distance traveled, okay, the distance traveled by a particle. Suppose it need to move in this direction, the distance, okay, whatever the distance comes under this motion, the particle along the direction of the magnetic field, along the direction of the magnetic field, in one period of revolution, okay, in one period of revolution of the circular motion, this is called as a pitch of the helical path. So pitch of the helical path, it is along the direction of the magnetic field, that is horizontal direction. We will write it as pitch of the helical path, that is 2 pi m into v into cos theta, that is along the direction of the magnetic fields. So that's why that is cos theta, that is horizontal direction. Okay, horizontal to the magnetic field, is it or not? Okay, so this is all about the pitch of the helical path. So dear students, uh, this is enough for your today. So motion of a charged particle with velocity v bar perpendicular to b bar. So whatever the concepts related to this concept is, I have said you, and the application type of question, that is cyclotron, an expression for kinetic energy, uh, frequency, time period, and also angular velocity, etc. That some kind of application, that is helical path of a charged particle, that is at an angle less than 90 degree. Okay, so what is pitch? I have said you. So in the next session, I'm going to explain about the further concept related to your syllabus. Okay, I hope this concept is related to you. So I'll explain deeply with a few problems related to the concepts. Okay, that may come to your CET and NEET examinations. Okay, I'll discuss in the next session. So I'll explain theoretically about what is the physical phenomenon related to the syllabus, then only you can easily solve the problems related to that concept. So that's why I'm going to handle with the problems. Please don't worry. So by this, I'm going to wind up the session for today itself. I hope this concept is clear to you. Please note down whatever I have taught in the class, and please don't forget to subscribe our channel and learn the things easily and as quickly as possible, because if you make hurry in doing so, you will get confused in that section or in that part of area. So please understand the concept clearly, whatever I have taught in the class, and make the notes of yourself, and it may help in the examination point of view. Okay, so let me wind up the session. Thank you.